680.25b2 of the National Electrical Code states that an ungrounded electrical system shall be permitted where the circuit originates in a transformer or generator having a grounded secondary source. 250.32 bone requires that an ungrounded electrical system shall have at least one equipment grounding conductor run with the circuit conductors and connected to the grounding terminal or enclosure of the equipment. In an ungrounded electrical system, the equipment grounding conductor serves as a return path for fault currents and protects personnel from electric shock. To meet the requirements of 250.32 bone, the equipment grounding conductor must firstly be sized according to the NEC table 250.122, typically number 10 AWG copper. Secondly, be connected to every equipment enclosure, outlet box, and other point where a grounding connection is required in a conventional grounded system, for example, a water pipe. Thirdly, be installed with the circuit conductors. Fourthly, not be connected to a grounding rod or other external grounding electrode. To implement an ungrounded electrical system under 680.25b2 and 250.32 burn, you need to verify the transformer or generator. Ensure that the transformer or generator supplying the circuit has a grounded secondary source. Size and install the equipment grounding conductor by installing an equipment grounding conductor of the appropriate size and connect it to all required points in the electrical system. Avoid grounding rods by not connecting the equipment grounding conductor to a grounding rod or other external grounding electrode. Consider using ground fault protection by installing ground fault circuit interrupters to provide additional protection against electric shock. It is important to note that ungrounded electrical systems should only be implemented by qualified electricians who thoroughly understand the NEC requirements and safety implications of such systems. Table 250.122 provides the minimum size of equipment grounding conductors for grounding raceway and equipment. The size of the equipment grounding conductor is based on the rating of the overcurrent protective device in the circuit ahead of the equipment. For example, if the overcurrent protection is rated at 20 amps, the minimum size of the copper equipment grounding conductor is number 12 AWG. If the overcurrent protection is rated at 60 amps, the minimum size of the copper equipment grounding conductor is number 10 AWG. If the overcurrent protection is rated at 100 amps, the minimum size of the copper equipment grounding conductor is number 8 AWG. If the overcurrent protection is rated at 200 amps, the minimum size of the copper equipment grounding conductor is number 6 AWG. If the overcurrent protection is rated at 400 amps, the minimum size of the copper equipment grounding conductor is number 3 AWG. If the overcurrent protection is rated at 600 amps, the minimum size of the copper equipment grounding conductor is number 1 AWG. If the overcurrent protection is rated at 800 amps, the minimum size of the copper equipment grounding conductor is number 1/0 AWG. If the overcurrent protection is rated at 1000 amps, the minimum size of the copper equipment grounding conductor is number 2/0 AWG. If the overcurrent protection is rated at 1200 amps, the minimum size of the copper equipment grounding conductor is number 3/0 AWG. If the overcurrent protection is rated at 1600 amps, the minimum size of the copper equipment grounding conductor is number 4/0 AWG. If the overcurrent protection is rated at 2000 amps, the minimum size of the copper equipment grounding conductor is 250 kcmil. It is important to always consult the latest edition of the National Electrical Code and local amendments for the most up-to-date requirements. Properly sizing and installing the equipment grounding conductor is critical for safety in electrical systems, especially ungrounded systems. The equipment grounding conductor provides a low impedance path for fault current to return to the source, which helps to quickly trip the overcurrent protective device and clear the fault. This minimizes the risk of electric shock and equipment damage. In addition to sizing the equipment grounding conductor according to Table 250.122, it is also important to ensure that all connections are made properly. Connections should be tight and corrosion-free to ensure a low impedance path. The equipment grounding conductor should be run with the circuit conductors in the same raceway or cable. This helps to minimize impedance and ensure that the fault current returns quickly to the source. As mentioned previously, the equipment grounding conductor in an ungrounded system should not be connected to a grounding rod or other external grounding electrode. This is because the purpose of the equipment grounding conductor is to provide a path for fault current to return to the source, not to dissipate the fault current into the earth. Connecting the equipment grounding conductor to a grounding rod could actually create a shock hazard by providing a path for current to flow through the earth. Ground fault circuit interrupters are an important safety device that can provide additional protection against electric shock. GFCIs work by monitoring the current flowing in the circuit and detecting any imbalance between the hot and neutral conductors. If an imbalance is detected, the GFCI will quickly trip the circuit, cutting off the power and preventing electric shock. GFCIs are typically required in wet locations such as bathrooms, kitchens, and outdoor areas. They can also be used in other areas where there is a risk of electric shock. When installing an ungrounded electrical system, it is important to carefully consider the specific application and to consult with a qualified electrician. Ungrounded systems are not appropriate for all applications, and they can be more complex to install and maintain than grounded systems. However, in some cases, an ungrounded system may be the best option for providing safe and reliable power. For example, ungrounded systems are often used in critical applications such as hospitals and data centers, where it is important to maintain power even in the event of a ground fault. The NEC provides detailed requirements for the installation of ungrounded electrical systems. It is important to carefully follow these requirements to ensure that the system is installed safely and correctly. Some of the key requirements include the following. Firstly, the ungrounded system must be supplied by a transformer or generator with a grounded secondary source. Secondly, the equipment grounding conductor must be sized according to Table 250.122 and installed with the circuit conductors. Thirdly, equipment grounding conductor must not be connected to a grounding rod or other external grounding electrode. Fourthly, ground fault protection may be required in some applications. Ungrounded electrical systems offer several advantages over grounded systems. One advantage is that they are less susceptible to nuisance tripping of overcurrent protective devices. In a grounded system, a ground fault can cause a large current to flow through the grounding conductor, which can trip the overcurrent protective device. In an ungrounded system, a single ground fault will not cause the overcurrent protective device to trip. This can be an advantage in critical applications where it is important to maintain power even in the event of a ground fault. Another advantage of ungrounded systems is that they can provide better protection against electric shock. In a grounded system, a person who comes into contact with a live conductor and ground can receive a severe electric shock. In an ungrounded system, a person who comes into contact with a single live conductor will not receive a shock unless they also come into contact with another live conductor or ground. However, it is important to note that ungrounded systems are not inherently safer than grounded systems. In fact, ungrounded systems can be more dangerous if they are not installed and maintained properly. It is important to ensure that all equipment is properly grounded and that ground fault protection is provided where required. In summary, 680.25 B2 permits ungrounded electrical systems under specific conditions requiring compliance with 250.32 born. This involves properly sizing the equipment grounding conductor according to NEC Table 250.122, connecting it to all necessary points within the electrical system, ensuring it runs with the circuit conductors, and avoiding connection to grounding rods or external grounding electrodes. Ground fault protection like GFCIs should also be considered. These systems should only be implemented by qualified electricians who understand the NEC requirements and safety implications. While ungrounded systems offer potential advantages like reduced nuisance tripping and potentially better shock protection, they must be installed and maintained properly to ensure safety. Always consult the latest edition of the National Electrical Code and local amendments for the most up-to-date requirements.